Let me see here. Okay, so today, what we're gonna do. First thing first, right? I corrected reports for labs 2 and 3, right? Now, report for labs 4 and 5 are due now. Okay, and today is going to be, let's see here. Really? I see. Okay. Okay, so let me see. Let me address some of your concerns. Okay, so let's see here. Today is 11th November 16th 2022, right? Here you go. Today is lab 6. What else? Okay, we will finish chapter 11, right? There's a chapter on the fluids that we started last time. Yeah, chapter 11. Today we finished chapter 11. Let's see what else we're going to do. We will have a quiz in 1 hour, more or less in 1 hour. Okay, we have a quiz in 1 hour. I posted, what did I post? I posted not this one here, this one. Homework for chapter 11 and 12. Okay, I posted homework for chapters 11 and 12. And let me see, someone just told me here that you have only one attempt. Let's see here. Okay, does anybody else has been having this problem too? The homework, you are getting only one attempt. Let's see, I just checked the settings of my homework, and it shows that you have more than one attempt. Let's take a look at this one here. Edit assignment settings. And let's see here, load. More students coming. Let me see here. Admit all, more people. Okay, here you go. So is anybody else having this problem with the why? Okay, which homework? Chapter 11 and from chapter 8. Anybody else in addition to Michael and Lily? Anybody else has a problem? I want to hear from the other students as well. Let's take a look at the assignment of chapter 8. Okay. More students coming. I did assignment settings. I'm not hearing from anybody else. Does anybody else have any problems with chapter 8, 9, and 10 with the number of attempts? Arthur, okay, we had that problem as well, right? Let me see what happened here. I was just posting the homework for chapter, the last 2 homeworks. I didn't have any problems. Now let's see, yes, mastery, no details. Notify into everyone. Okay, load this too. Let me take a look. Come on, man. Student view 8, 9, and 10, right? So let's see here. Master copy share to commons. More students coming in. Well, I can't seem to find the place where I check for that settings, but I'll look into that. Okay, I'll look into that. So just remind me next time. Yeah, when I click it here, I don't see. Let me see. Edit assignment settings. It doesn't let me go. Let me see. Points assignment. Maybe it's here. No. Wiley plus add. Yeah, see, it doesn't have the. Should have already submitted homework on this assignment. Yeah, but anyway, when I submitted the latest homework, I did note that there was like 3 attempts for those 2. Okay, so yeah, yes, email me a picture. Yes, so I can look more closely on that. Now let me see. There is another student here that mentioned my group. Okay, I believe you meant that your group is group 7. Is that right, Vahag? Not lab 7, but group 7. Okay, and which lab are you talking about? Lab 3. Okay, lab 3. So let's see what. Let me stop sharing. Group 7, lab 3. Let me take a look here. Group 7, lab 3, spreadsheets. Okay, yes, I am able to see your graphs, no problem here. Okay, now let me take a look at your correction here. Corrected. Lab 7. If I took out points, it was not, you know, if I took out points, it was not because I couldn't see the graph. Okay, but because it was because of something else. Okay. Okay, I took out points. I did see your graph. Okay, Vahag. I did see the graph of your group. And there was some mistakes there in the graph that I took out points from it. So yes, I could see your graphs in there. So I didn't, you know. So I did, if I took out points, which was not because I could not see your graph, but because the graphs were not properly displayed. Okay, that's yeah, we can discuss that after class. Now there's more students coming here, and now let's finish chapter 11. Okay, and I will give you a brief introduction of today's lab, and just after the brief introduction of today's lab, we will do the quiz. Okay, quiz 11. So let's get okay, quizzes, lecture notes right in here. I corrected lab reports for lab 2 and 3. Reports for lab 4 and 5 are due now. Today is lab 6. We'll finish chapter 11. We'll have a quiz roughly in 1 hour. Quiz 11. Quiz 11. I posted homework for chapters 11 and 12. No, it's not chapters 11 and 12. It's chapters 10 and 11. And let me share this screen as well. Okay, here you go. You're sharing the screen. Good. More students coming. Here you go. Also home and not this one here. Yeah, that's chapters 10 and 11, not 11 and 12, but 10 and 11. Chapters 10 and 11. Okay, so just review. Today's quiz is going to be on the material that we covered last time, the material we're going to cover today. Okay, so 5 questions. Okay, we have a quiz 1 hour with 5 questions. 5 questions, just like before. 15 minutes long. So don't forget chapter 11, what we're going to cover in chapter 11. Chapter 11, we're not covering everything. We're covering 11.1, 11.2, 11.3, and 11.6. Okay, so what's chapter 11.1? Oh, 11.1 is density, mass density. You specifically state mass density in there because there are other types of density. But every time that we talk about density, we mean mass density. In 11.2, we covered pressure. Okay, the idea of pressure, the concept of pressure, which is a very useful one. 11.3, what did we cover? We cover, there you go, pressure and depth in a static fluid. Okay, pressure and depth in a static fluid, very important. Static fluid, and don't forget we are talking about the static here. If the fluid is moving, then you have a correction for the pressure due to the motion of the fluid. Okay, I'm going to give you a very simple example so you can understand what happens. Okay, the quiz again. The quiz is going to be based. The quiz is based on last last lecture meeting, and today's meeting. Okay. Now pressure. Now here you go. Let me stop sharing momentarily. Here you go. At this very moment, I have this huge column of air waiting on my hand, not just on my hand, but in my head as well. Okay. If this air is static, if it's not moving, if there is no wind whatsoever, what I have here is a static pressure. Okay, I don't feel that weight of the air. Okay, because we already grew accustomed to that. We already grew accustomed to this pressure. Okay, now suppose that you have wind blowing in my hand. Okay, like I'm going to do that. Okay, so the moment that I make a fluid move, and wind is a fluid, air is a fluid, I feel that pressure due to the motion of the fluid. That's what we call dynamic pressure. We're not going to cover that. Okay, and that's why we have to distinguish dynamic pressure from static pressure. Okay. In aviation, we call this pressure not dynamic pressure, but we call it room pressure. Okay, so that's why the guy is specifically, that's why the book specifically states that it's a static fluid. Yeah, we calculate the pressure due to a static fluid. Now, we didn't calculate the pressure due to a moving fluid. Okay, we are not going to cover that. And the last one here is the Archimedes principle. Archimedes principle. That's what we are covering for those for this chapter, those 4 sections of this chapter. Okay. At this point, you should already know how the pressure varies with depth in a fluid. Okay. In the case of, we did that for water, but it also applies to other. It also applies to other types of fluids too. Okay. But let's talk about Archimedes' principle. What is Archimedes' principle, okay? And then once we are done with this Archimedes' principle, then we can start moving to the lab, right? I'm gonna brief you quickly on what the lab is about today. And then after this briefing on the lab, we're gonna do the quiz, okay? So here you go. Let me go consider a container, okay? A container. We go ahead and pour water inside this container. Okay. Remember that above the water, we have this column of air that's exerting pressure here at the surface, right, of the water. And this pressure is 1 atmosphere. You don't see? Oh, I'm sorry. Yeah, let's start again. Thank you. Thank you, Janet. Here you go. Let's start again. Now you see it, right? Sometimes I turn off the sharing and I forget that I turn off the sharing. Feel free to remind me of that, okay? Do you see now? Do you see now that? Do you see the screen now, Janet? I presume you all see it.
Yeah, we can see it.
Okay, yeah, your voice is coming very low here. My speaker, yeah. Let's see here if I can adjust it. Good. Okay, so let's start again, right? We have a container, a vessel, that we pour out water inside this vessel. And we need this system to understand what Archimedes' principle is all about. Archimedes was one of the, I would say one of the greatest genius of humankind. Okay, I think that guy was the brightest of all, brighter than Einstein, brighter than Kepler, brighter than Galileo. You know, this guy was back in the ancient Greece, and he discovered some amazing things. He almost came about to invent in calculus, integral calculus, which was, by the way, was invented only 1900 years after himself. Okay, that's how bright he was, and he came very close to invent calculus, integral calculus, something that Newton himself invented in the 1700s. So we go ahead, we have this container with water, right? And we have this column of air at the surface of the water. I am representing the pressure of the air by those downwards arrows. The atmospheric pressure is 1 atmosphere, 100,000 newtons per square meter, or 100,000 Pascal, right? And below the surface of the water, we have, let's see if that's what I want. Yeah. Okay, yeah, I don't want to do that. Let's see here. Okay, I want this one. Yeah, below the surface of the water, right? We have that pressure that I derived for you. Okay, the pressure due to the column of water itself. The column of water itself contributes an additional pressure in addition to the air pressure, right? And we did a derivation for the pressure due to this column of air, and we found out that the pressure goes with the goes up linearly with the depth. Okay. So share. One more student's coming. Here you go. Well, now consider an object that is submerged. And remember the result that we got here, right? The pressure increases linearly with the depth. Okay? The pressure here at this point is smaller than the pressure here at this point, which increases, and so on. Okay? So now consider an object that's submerged. Archimedes discovered this principle of his after the king asked him to find out a way to determine whether his crown was made of pure gold or not. Okay, and at that time Archimedes has to think very hard, and the idea goes that he was having his bath at home in his bathtub, And he was not thinking about the problem. He was just worried about having his bath. But just by submerging his body in the water, he noticed that the water displaced, right? There is a displacement of the water whenever it becomes submerged in the water. And that when that flash of genius came to his head, and he screamed, "Eureka!" Eureka means I found in Greek, right? And what's the idea that he came up with? Okay, so consider this object that's submerged here. Let's see. Okay, this object is submerged. We have the atmospheric pressure being applied to the surface of the water, and we also have the atmospheric pressure plus the pressure of the water being applied to the object here at the top of the object. As you know, the pressure goes down, goes up linearly as you go deeper and deeper, right? Can you picture that? So here, those arrows are not in scale, okay? Those arrows are not in scale. If I were to do it in a proper way, this atmospheric pressure would have to be smaller than everybody else, right? Here you go. Smaller. Smaller. Right, here you go. This arrow here is longer than those other ones because we have this column of water that's above it. This arrow should be almost the same length as this one, okay? But the pressure increases. Let me make it a little bit longer. Increases linearly with the depth. Okay. So on the side of the object, we have this side pressure. This pressure goes to the side, and then on the other side, we also have the same pressure because of the same depth, right? So the pressure here on this side is exactly the same as the pressure here on this side because it's exactly the same depth. Because of that, the pressure, the force due to the pressure cancels out in this horizontal direction, whether it's at this point, whether it's at this point, at this point, or this point, okay? So the net force due to the static pressure of the fluid cancels out in the horizontal direction. But what happens at the bottom? Something interesting happens at the bottom. The pressure at the bottom is greater than the pressure at the top. So we do not have this. So we end up having this pressure differential between the bottom and the top. Okay, remember, pressure is this funny type of force that acts in every possible direction, not just in the vertical direction like the weight does, okay? Like the weight is a force that acts only in the vertical direction, but pressure is a force that acts in every possible direction, every direction that is perpendicular to the surface. Even better, that's normal to a given surface. Okay, so let's write that down. Let's cover Archimedes' principle now. Let's cover Archimedes' principle now. Okay, last meeting, we found that the pressure, the static pressure in a fluid increases linearly with the depth. Okay. So if you have an object submerged in a fluid, it will be subjected to a pressure from every direction, top, bottom, and sides, okay? Top, bottom, and sides. Because the pressure is higher below the object, we are going to get a pressure differential between the top and the bottom of the object. This pressure differential results in a net upward force. Okay, that's the first thing you have to know about Archimedes' principle. Okay, notice that we have more pressure here at the bottom than at the top, right? What does it mean? It means that we are going to have a net pressure that's upwards, which results in a net force due to the pressure of the fluid upwards. This upward force we have a name. It's called the buoyant force. Okay, that's why I put the B here. Here you go. In a net upward force, this net upward force we call the buoyant force. Okay, that's why when we are submerged in water, we feel lighter, okay? Because we're subjected to this buoyant force. That's the reason we feel lighter, because the pressure at your feet is higher than the pressure at the other parts in your body, and you're being subjected to this upward force. Okay, so that's what you have to know, buoyant force. That's the first thing that you have to know about Archimedes' principle, the buoyant force. Okay, that is the first thing you have to know about Archimedes' principle, the buoyant force. Okay, then there is one more thing that you have to understand about this principle. What else you have to know? Okay, so we're gonna go back to our vessel, right? Here you go. Here's the object before it was submerged, right? Here's the liquid. Here's the interface between the liquid and the air is at this position. But when you submerge the object, what happens to the interface between the air and liquid? It rises. And there's a good reason for that. Okay? And if you go ahead and calculate this volume here, the volume of water, we call it the displaced water, volume of the displaced water ends up being equal to the volume of the object as well. This is a basic principle in physics, okay? Two objects, the water and the object itself cannot occupy the same place at the same time, okay? They cannot be co-located simultaneously, right? That's why you have this displacement of the water. And that's what Archimedes himself observed when he was bathing himself at home. Okay, so now we have those two important ideas. One, the buoyant force. And the second important idea is that a submerged object displaces a volume V. Okay, a submerged object of volume V displaces the same volume of water. Let's put it this way, a completely submerged object of volume V displaces the same volume of water. Okay. So now you have those two ideas that apparently they have no connection whatsoever. But then Archimedes recognized that there was indeed a connection between those two. What did he discover? And I'm going to formulate his discovery here at the time. At the time he had to, pick up this idea. And Archimedes in possession of these two pieces of information, Archimedes was able to determine the value, the numerical value, right? The quantitative value of the buoyant force. Okay. At this moment, at this very moment here, all we know that there is a buoyant force, but we do not know what its value. But by putting together those two pieces of information, he came up with his Archimedes principle, which is formulated as, the buoyant force is equal to the weight of the displaced fluid. Okay, the buoyant force applied to an object is equal to the weight of the fluid displaced by this object. Displaced, and the buoyant force applied to a submerged object is equal to the weight of the displaced fluid. Okay, that's what the principle that he came up at the time. At that time, he had to think very hard about this principle, but today with the mathematical tools that we have, which includes algebra, we are able to derive the so-called principle. Okay, Archimedes himself didn't have algebra to help him out come up with this conclusion, but today we can prove mathematically that's exactly what happens when we have a submerged object. So what does it mean, Archimedes principle? It means that if you go ahead, collect this water here, this amount of displaced water, this volume of displaced water, you determine its mass, multiply by the acceleration of gravity, the weight of this displaced volume of water is going to be equal to the buoyant force. Okay. So that's what I have here that you have to memorize. Okay, so here you go. Let a volume V of water being displaced. Okay, the buoyant force being applied to the submerged object is going to be given by the following formula. Here you go. Buoyant force B, weight of the displaced fluid. Let's put it this way, okay? The weight of the displaced, even better. I'm gonna put like that, displaced fluid, and it's gonna be equal to what? It's going to be equal to the mass of the displaced fluid times the acceleration of gravity. And then we can go further. We can go even further than that. Remember that the mass of the object is related to the density of the mass of the displaced water, right? The mass of a substance is related to the density of the substance. So we can write that down as being rho of the displaced liquid times the volume of the object times G. Okay? So that's what the buoyant force is all about. That's what the buoyant force is all about. Okay? If the fluid is water, right? Is water, then its density, you already know, then its density will be what? Will be a 1,000 kilograms per cubic meter. Okay, here you go, 1,000 kilograms per cubic meter. So suppose, example, simple exercise. Find the buoyant force applied to an object that is a volume that has a volume of 1 cubic meter. Okay. Find the buoyant force applied to an object that is applied to an object of 1 cubic meter. Okay. That, very important, that is completely submerged in water. Okay. 1 cubic meter object that's completely submerged in water. Don't forget, I put it completely. The object can also be partially submerged, right? If the object is partially submerged, you have to find out what the volume of that partial submerged volume to find out the buoyant force, but that's not the case. The completely submerged, is a completely submerged object. All you gotta do here is to use the formula of the buoyant force, right? Here you go. Mass of the displaced fluid is going to be the volume of displaced fluid times the volume of displaced fluid, right? Which, by the way, is equal to the volume of the object that's submerged, because the object is completely submerged. Here we're going to have 1,000 kilograms per cubic meter. We are going to have 1 cubic meter of volume, and I'm going to approximate that. I hate when that happens. I'm going to approximate the acceleration of gravity to 10 meters per second square, right? And now we can go ahead and do this mass. It's going to be 10,000. 10,000. I'm multiplying. Let me see. Yeah, cubic meter cancels out this cubic meter, right? We end up with kilogram only. And as we expect, what you have here, you have kilogram meter per second square, right? Which is nothing but newtons. Okay. So a 1 cubic meter object is going to have this much buoyant force if it becomes completely submerged. What comes next? Okay. What comes next is also interesting. It's also interesting, right? Under what conditions? Here you go. Under what conditions will this object, 1, sink, 2, float, and then there's this third condition as well that we call the become neutrally buoyant. Have you ever heard of that? Become neutrally buoyant. Everybody knows what sinking and floating means, right? But there is this other condition too that is similar to floating, but it's not exactly the same, which we call neutrally buoyant condition. Okay, so let me give you an illustration here. Here you go. Here is the case of an object that floats, right? I completely submerge the object and then it tends to move upwards. It tends to float. Okay, and as it floats, the volume of the water changes. Do you see that? Do you see here? I did that on purpose. Oh, I did that on purpose. If the object sinks, what's going to happen? Here you go. If the object ends up sinking, it's going to move downwards. And that volume of water won't change at all. Here you go. An object that sinks. And the other condition that you might not be, the pressure becomes higher as you go deeper and deeper, right? The pressure here at the bottom is higher than the pressure here at the top, right? But the pressure differential between the bottom and the top remains the same. The pressure differential, the pressure here at the top minus the pressure at the bottom is going to be the same no matter how deep you dive. Okay, make sense? Let me put up. Yeah, here you go. Go up, right? So here you go. Here you go. Go down, down, right? So the pressure differential, the difference between the pressure at the top and the bottom is going to be the same at this point than at this point. Okay, it doesn't change because it goes linearly, right? We can prove that. We can prove that easily mathematically. Delta P is the same no matter how deep you dive, provided, of course, you don't change the shape, right? Provided, of course, this object doesn't change its shape. If the object changes its shape, then the story is different. Okay, and then we have this other condition. If you practice, scuba diving, you know what I'm talking about, right? Anybody here practice scuba diving? Huh? Now, the condition of neutral buoyancy. What's the condition of neutral buoyancy? In the condition of neutral buoyancy, an object that's placed at this depth remains at this depth. Okay? That's what the condition of neutral buoyancy. Okay? Object that floats, here you go. Oops. Object that floats, right? Object that remains neutrally buoyant. What happened to my sinking object? Oh my goodness, I lost it. Yeah, okay, I'll have to do that all over again. Let's do that again. Neutrally buoyant, right? Huh. Mystery. Let's do that again. Here you go. Here you go. Looks like I accidentally deleted that set of the slides. Here you go. Sinking object. Okay, so here you go. Let's do it again. An object that floats, right? An object that remains neutrally buoyant. Fishes are very good at remaining neutrally buoyant. Okay, and scuba divers, sure, if you practice scuba diving, you learn how to remain neutrally buoyant underwater. And here is an object that's sinking. Okay. What are the question is, what are the mathematical conditions for those three situations? Okay. What are the mathematical conditions for those three situations? Okay, so here you go. Here's the case of the object that sinks. Sinking object. For the case of a sinking object, the weight must be greater than the buoyant force. Sinking object. The weight must be greater than the buoyant force. If the weight is greater than the buoyant force, then the object is going to move downwards. We have that, see, velocity. That's the net force, right? And that's the velocity of the object. Here, I'm not taking into account. I'm neglecting the the force of the fluid friction, right? The fluid friction, the friction due to the fluid. Here's the case of an object that floats. The buoyant force is greater than the weight. Okay. If you have something like that, the net force is going to be upwards and the object is going to move upwards, just like you saw before. So I can put it here in my drawing, right? Here you go. Object sinks. Let's do that. Object is 1, 2, 3. Oh. Here you go. Object sinks, right? Net force is equal to that. So the object is going to sink. Sinking object. Net force downwards. Object is going to move downwards. Okay. Now we can go for the next one. The next one is a floating object, right? 1, 2. Here you go. An object that floats has a net force upwards, right? Consequently, it's going to move upwards. Just like the arrow indicates. Okay. And now the neutrally buoyant object doesn't change its position. In this case of the neutrally buoyant object, the weight is equal to the buoyant force. The net force is 0. Consequently, there will be no net force and the object is going to remain at the same position. Okay? In this case, right, for the floating object, the pressure decreases upwards, right? In the case of the sinking object, the pressure increases downwards. Now, so based on those ideas, we can now come up with some pretty neat conditions to achieve neutral buoyancy, to achieve buoyant, to float, and for an object to sink. Mathematical conditions, okay? So here you go. Let's go. An object that sinks, has a weight that is greater than its buoyant force, right? So the mathematical condition is the following. Sinking object, mg minus b is going to be greater than 0. Okay, so here, that's the mathematical condition. Let's see if we can do more than that. Let's see if we can do more than that, right? Remember that the buoyant force is what? Is the mass of the displaced fluid times the volume of the displaced fluid, which, by the way, is equal to the volume of the object itself, right? Oh, sorry, it's not the, no, sorry, let's do that. Mass of the displaced fluid times the acceleration of gravity. Okay, that's what we want to do. What's the next step? The next step is we're going to rewrite the mass of the object, mass of the displaced fluid as the density times the volume of the object, which is completely submerged. Sinking object that is completely submerged, right? Completely submerged means V displaced must be equal to V. Go. One more student coming. Okay. Well, we can do more. We can do more than that. We can go ahead and rewrite the mass of the object in terms of its density and its volume as well. But now the density of the object is going to be different from the density of the substance, right? And now look what we get. We get two terms here that are exactly the same, volume and the acceleration of gravity, right? We can put them in evidence. You go. Put them in evidence. And then for an object to sink, what's the condition? What is the mathematical condition for this object to sink? Its density must be greater than the density of the displaced fluid. That's the condition. If you know the density of your object, you know the density of your fluid, and the density of your object is greater than the density of your fluid, then the object is going to sink. Then we can repeat the same thing for an object that floats. Floating object that initially is completely submerged, right? Now what happens? What happens is that the buoyant force is going to be greater than the weight of the object. That's the only thing that changes in this equation. Okay, here you go. Everything else doesn't change at all. See that? Everything else remains the same, right? So that's the condition for the object to float. The density of the object must be less than the density of the fluid, like in the case of styrofoam. The density of the styrofoam is less than the density of water. For this reason, it floats. It floats. Okay. And then we have the other condition, right? Neutrally buoyant. Neutrally buoyant object. Buoyant object. So, for a neutrally buoyant object, the buoyant force must be equal to the weight, or the net force applied to the object is 0. Okay. For this inequation to hold, the density of the object must be equal to the density of the displaced fluid. Yes, that's right. Anything that floats has a density lower than the fluid. Okay, it's a relative thing. If the object floats, if the object floats in the water, it means that the overall object has an overall density that's less than the density of water. Okay. Yeah, and that's a very easy experiment that you can do at home, okay? You can get a solid piece of iron, right? Put on the water, it's gonna sink. But then suppose that you can make a vessel of iron, right? Not a solid, piece of iron, but a vessel of iron. You're gonna go, make a huge air volume, put a air volume inside that that iron, that piece of iron. Okay, depending how big is the air inside that gap in the iron might be able to float, because now the overall density is the density of the iron plus the density of the air, right? So we're talking about overall density, right? If you're talking about a solid object, yeah, the density of the object must be lower than the density of the fluid. That's what we have for this, for this chapter. And it's 9:49 right now. Let me take attendance. Let me take attendance, and then we have a little break. Okay, then I cover quickly the theory behind the lab today, and after that we have our quiz, right? And after the quiz we do the so-called lab. Now, what's going on here? Let's see. It says, okay, okay, 9. Okay, good. Insert. And doesn't like it. 16. Okay. Vanessa Bonilla, are you there? Yeah, thank you. Fisher, Dawn?
Here.
Thank you. Blessing, are you there, Blessing? I don't see Blessing here in my list. Next is Janet Garcia. She's here, right, Janet? Yes.
Yeah, I'm here.
Thank you. Ryan Ong.
I'm here.
Thank you. Mia Villalobos.
Here, Professor.
Thank you. Raymond Garcia. Okay, thank you. Joshua Jimenez.
I'm here, Professor.
Thank you. Lily Hassid. Thank you. Next is Michael. Thank you, Michael. Daisy Mariscal. Thank you, Daisy. Donia. Are you there, Donia? Okay, I'm gonna put a star here on Donia. I see her name here, but I don't hear from her. Jennifer Perez. Is Jennifer there? Let's see. Jennifer, I see her name here in my list. I'm gonna put a star as well. Elika Vape. I can't
Here,
hear
Professor.
you. Okay, good. Thank you. Artur Pacheco. Thank you. Brianna Valencia. Brianna, are you there, Brianna? Doesn't look like Brianna is in front of her computer. Let's see, next. Mary Okiki.
Yeah, Professor.
Okay, Basilio Lopez. Good. Vahag. Okay, Alejandra Marmolejo. Let's see, I don't see Alejandra here. Amarilis Mejia.
Here.
Thank you. Next is Yesenia Montes Rodriguez. Okay, good. Yesenia. Justena Youssef. Let's see here. Yesenia. Okay, good. Yesenia is here. Jade Esquera.
Here.
Thank you. Ashley Diaz.
I'm here.
Okay, and Lebilud. Good. So we have how many students here? 21, 22, 3 students didn't answer. Let's see. Donia, are you there, Donia? I don't hear from Donia. Jennifer Perez, I don't hear from Jennifer. Okay, and the last one is Brianna Valencia. Okay, so good. So let's 9:53 right now. Let's have our break. Let's have our break. You might want to quickly review the material that we did last time that we met, right? So, and once we join again, I'm gonna briefly review the theory behind that. And after reviewing the theory, we're gonna have our quiz. Okay, so here we go, quizzes, notes, here we go. Break 9:55 a.m. to 10 a.m. If you don't have any question, label it. Okay. If you don't have any questions, I see you in 15 minutes. Okay, I'm back here. Let's start sharing the screen again. Lab notes, good. So let me review here the, let me see here. I didn't download the spreadsheet yet, lab 6, okay, so hang in there. So today's experiment is on uniform circular motion. Like I said, I'm going to brief you quickly in the theory behind this so-called experiment. Okay, don't forget lab 4 and 5, right? Reports for lab 4 and 5, or labs 4 and 5 are due now. Let me download the spreadsheet for lab 6 now, so I don't forget. Let us follow this recipe, right? For data lab 6, let's make sure everything is fine here. I gotta change 06. Little 6. 06. Oh. You had said only 4 was good. Now we did, let me see. One minute, let me check. When did we do lab 5? Let me check here. We did lab 5. Yeah, we did lab 5 a week ago, right? So it was lab 4 that I postponed, okay? 1 week. So lab 4 and 5 are supposed to be due now. And did I lab notes? Yeah, reports for lab 4 and 5 are due now. See that? Those are my notes, lecture notes, and those are my lab notes. Yeah. Okay, so now let me continue here in my okay, so I have everything here ready to go. I'm going to upload this report, this spreadsheet to your group folder. I'm in Google Drive. Google Drive. Oh, big 6 group folder. Now, group 1, group 2, group 3. Don't forget it's okay. Group 3, group 4, group 5. Let me see if it's getting there. Group 5, 4, 5. Okay. Okay, group 1. Don't forget to relabel this document. Okay, otherwise I'm going to start taking out points. You're supposed to label it in the same way that you labeled your spreadsheet. Okay. Rename it. Okay, here you go. Because it's a lab 4, group 1. Okay. Gotta rename it the same way you name it. You gotta name it the same way you name your spreadsheet. Keep the PDF in there, okay? I need you, please do that. For the other one, group 2. Let's see, I don't see lab 6 here. Strange. Let me see if lab 6 copied there too. Lab 6 copied here. Lab 6. Yeah, I don't see lab 6 copied in here. Strange. Replace. Okay. So it's in there. Okay. Okay, that's because this guy here. Yeah, I've got to relabel that. Okay, Mia. Lab 5. Okay,
Oh, Professor,
Mia. Yeah.
for that one, it's showing as a 1 because it hasn't replaced like the document that you put in for lab 5.
Are you talking about this one here?
Yeah. So it has a 1 because there's still your Excel spreadsheet for 5.
Okay, but you gotta change. It's not P37, it's P06, okay?
Oh, okay, got it.
Okay. That what needs to be fixed. So you choose which one you want to keep. If you want to keep this one or this one, okay? Which one I'm not going to correct both of them, okay? Okay, so 3. Okay, good. Lab 6, 3. Good. Lab 4. Yeah. Okay. 5. 6 L06. Yep, same thing here, right? Group number 5, you gotta rename it. That's yeah, I gotta rename it P06. Group 5, group 6. Yeah, same problem here, right? So, lab 06. Okay, that's group 6. Good. Group 7. Group, why I don't have group 8 here? Interesting. Group 8. Group 8. Group 8. Group 9. Oh gosh. Group 9. Group 10. And group 11. Okay, so I uploaded the spreadsheets. Report for lab number 6 is due next. Is due. Oh, by the way, next week is gonna be what? Next week. Next week. Yeah, next week is gonna be the exam, okay? Chapter 7 through 10, labs 2 through 5, okay? Okay, so let's see. So report for lab number 6 is due in 2 weeks. In 2 weeks. Since we are going to have an exam next week. Today lab is uniform circular motion. First part, we're going to use Senko centripetal force apparatus to study uniform circular motion. Okay, so it's uniform circular motion. Okay, we did that. We did the theory behind before, right? Let's go back here to the idea of uniform circular motion. in general, let me see, let me get a nice illustration here. Okay, I want to use this one right here. Okay, so here we go. So consider, you know, the X and Y axis, right? Consider X and Y axis, and consider also a position vector R that is describing the position of an object with respect to origin of the graph, right? So here you go, right here. Oh, what happened? Here you go, right here. Let me mark a dot. Yeah. That's the position vector. Let me erase this guy here. Okay. Okay, if this object is undergoing circular motion, not necessarily uniform, if this object is undergoing circular motion, okay, what does it mean to undergo circular motion? Let's see. Okay, rotation. Okay. To undergo circular motion means that the distance of the object to this origin is always the same. The vector position may change, but not the magnitude of the vector position, right? That's what it means. There you go. That's one position. That's another position, right? This distance right here, R, doesn't change at all. That's what it means, circular motion. And it doesn't matter if it's uniform or not. It doesn't matter if the motion is uniform or not. Okay, what else? What are the other consequences? Let me, here, I'm going to animate this thing, right? So this little object is undergoing circular motion, not necessarily uniform. As it undergoes circular motion, the distance of this point to the origin of your coordinate system does not change at all. That's what it means to undergo to undergo circular motion. Again, not necessarily uniform. And what else does it mean? Here you go. Oops. Here you go. Right? So here you go. Distance from the origin, distance of the point to the origin remains the same. Okay? So this object is undergoing circular motion. In this specific case, because the length of this vector doesn't change, we say that the object has only tangential velocity. Okay, let's write it down. An object undergoing circular motion, not necessarily uniform, has only a tangential velocity. Okay, so whether it is here you know, the velocity of this object is always going to be tangential to the path, which is circular, right? Which in this case is also perpendicular to the vector position. Okay, so right in here is going to be like that. Right in here is going to be like that. Like I said, the velocity doesn't have to be necessarily uniform. Okay, but the velocity vector is going to be perpendicular to the position vector because this motion is circular. So here you go. Tangential velocity vector, tangential velocity vector, and so on. One more here. Tangential velocity vector. Do we have another one? Nope, we don't. Okay, here you go. Okay, four frames. The object, here you go, has only a tangential velocity. Since it has only tangential velocity, comma, its radial or centripetal velocity is going to be 0, right? But that's for circular motion. What if it's not circular motion, right? What if it is, for instance, I'm going to draw here for you. Not circular motion, but elliptical motion. Okay, this thing here can be depicted as elliptical motion. And no fill right in here. At a given instant of time, my object is going to be here, right? Let me put it aside. Here's my position vector with respect to the center of my ellipsis. And this object is going, remember, the velocity is always going to be tangential to the path, right? In this case, not only are we going to have this tangential, a velocity component that is tangential to the path, but you also can break down this velocity vector into two components. One that is perpendicular to the position vector, right? And the other that is parallel, or let's say anti-parallel to the position vector. This one I call it the radial velocity component, the component of the radial velocity. Okay, I'll put them in red. Okay, so, but that's the type of velocity, that's the type of motion that we are talking about, the circular motion. Okay. In general, here we go. In general, a particle has a radial velocity in general, but radial velocity component, but not if the motion is circular. Okay. And if you have a situation like that, you're going to have a centripetal. If you have a circular motion, you're going to have a centripetal acceleration That's V squared over R. Okay. So let's see here. That's what I want to tell you before we do the quiz. Let's see here. Yeah. Okay. So let's do the quiz now, and it's 10:31 right now. Okay. Let's start the quiz at 10:35. Let me go here to. So that's all I want to do. I want to remind you of the ideas of circular motion. Okay. Having said that, we can go ahead and do the quiz number 11. Let me edit it. We're gonna start at, today is the 16th, 11:30, 10:35. We're gonna do, let's see, it's 3 questions, it's 5 questions. We're gonna do 3 minutes each question. Okay, 15 minutes. So 35, 27 and a half. Okay. Okay, thank you, Donia. 10:35, let me put it available 10:35 here. 10:35 a.m. Gone. When is it going to be due? 17 minutes from 10:35. That's 15, 30. Okay, 10:50. 10:50. 10:50 a.m. Okay. 10:35 is going to be in 2 minutes, so get ready. 10:50. And I'm going to start displaying. I'm going to publish that and check if you can see the quiz 11 there. Right, I can see quiz 11 here, November 16, 10:35. Okay, I'll give you a little, I'm going to display here the questions. So you're going to have like a 2-minute head start, right? Here you go. You can start thinking about this question, the answers to those questions. And like I said, you have a 2-minute head start with respect to the quiz in there. Am I displaying the? Yes, I am, right? Okay, good. It's material that we covered on Monday and today. Let's check here, student view. Let's see, quiz not available until, okay, it's gonna become available in 1 minute. Let me leave student view. Let me go back to displaying the quizzes, the question of the quiz questions. What the heck is doing? $10:35, that should be available. The quiz should be available right now.
Professor, it's quiz 11, right?
Yes, quiz 11.
Right, and then do we start right now?
Yeah,
All right, thank you.
yeah, you're right. Last 1 minute. Strange.
Wait, Professor, it's saying that I only have 20 seconds left on my quiz for 5 questions.
There's something wrong there. It's who is that?
Donia.
Donia? No, Donia. Everybody else here. It says in my computer program said here that you have 13 minutes left, not 20 seconds. Must be
Let
something
me
wrong.
double check because when I clicked on it, because I know I lost a minute, but oh, just kidding. I think it's just like restarting. Okay, never mind. Thank you.
Oh, Eight minutes. Okay, you gotta display the fifth question, right? I'm assuming that you already did the first two. Let's see, here you go. Now you can see everything. Hopefully it's large enough for you to see it. Finished. Okay. Quatro. 11. Answer those questions. Let's switch it. Okay, time is up for some of you. We're gonna go for another, 7 more minutes, okay? Hang in there. In this meantime, if you finished the quiz, you can take a little break, You. Let's see. We'll be starting soon, just hang in there. We're just waiting for one more student to finish. Okay, so we're done. Everybody finished, right? See here. Yeah. So now let's go for our lab. You already have, let me close this window. You already have your spreadsheet, and let me walk you through this experiment. Okay, so what we're going to do in this experiment, in this lab activity, right? We are going to show that this equation here is correct. Okay, that we derived that centripetal acceleration is v squared over r. You know, where v is the speed of the mass and r is the radius of the circular path. So what do? We measure we put an object to move in a circular fashion. We measure the radius of the circle that the object is undergoing, and we time how long it takes for the object to go a full circumference, okay? From this measurement of time, from this time measurement, we get 2 pi r and divide by t to get the velocity. That's how we do in this experiment, okay? And what else do we do? Okay, we are going to use the Newton's law, not only this equation for the centripetal acceleration, but also the equation for Newton's law, which is the mass of the object times its centripetal acceleration. The net force is mv squared over r, okay? So in the experiment, we measure the mass of the object using a scale that has a resolution of 100 of a gram. Every mass measurement that we do here in this class, okay, we use this scale here that has this resolution of 100 of a gram. So let's get our spreadsheet here so we can follow Okay, here's the spreadsheet. Okay, here is the mass of the object. It's a bob. It's a bob that we attach and put it to rotate in uniform circular motion. It has a mass here that you have to adjust the significant digits, right? And what else? You measure the radius of the circular path. Let me show you how we do that. Yeah, we measure the radius of the circular path, and we measure something else, which is the period, okay, of a number of revolutions. Instead of measuring the period of a single revolution, it is far more accurate, okay, and precise as well, not just accurate, but precise, to measure the period of 20 revolutions. Think about that, you know, get an object to move in circular fashion and count 20 revolutions. Count 20 revolutions and count how long it takes for the total number of revolutions. Okay. And the velocity is going to, for a single rotation, it's going to be 2 pi r over t. Okay. So once we find out the velocity of the object, and here you go, let's go get it here. The spreadsheet again, right? Let's see here. No, that's 3. We don't want that. We want this one here. Here is the radius of the object. Well, we do not change the radius of the object. And then what we do? We are going to keep on adding masses to this bob. Okay. Here we are adding 0 grams to the mass of the bob. We add 30 grams, 60 grams, and so on. Okay. And that's going to be the net mass of the object that's undergo uniform circular motion. Here's the period for 20 rotations. Here's the period for a single rotation. All of that is data. Let me see, data, right? Data, raw data, and raw data. That's the first part of our experiment. And before we move forward, let me play a movie that I have for you explaining this experiment. Okay, so let's see, this one, lab number 6. Had the chance to look at this video. It's a video that I'm very proud of.
Centripetal.
Let's see if I have enough volume there. Let me know if you can hear. Okay, this video explains how the experiment is performed, so you can understand how the whole thing goes. Okay, here you go.
Centripetal force experiment. Constant radius and variable mass. In this experiment, you will verify Newton's second law for an object under...
Oh, something wrong here. Let me start again. What's going on? There must be something wrong. Okay, what about now?
Centripetal force
good.
experiment. Constant radius and variable mass.
Okay, note that we are doing an experiment in which the radius of the object that's undergoing uniform circular motion is going to be constant. We are going to make like 6 different measurements, and we're doing those 6 different measurements. We're going to keep the radius the same, but we're going to change the mass of the object that rotates. Okay, that's why I put constant radius and variable mass.
In this experiment, you will verify Newton's second law for an object undergoing uniform circular motion. You will change its mass while keeping its radius of rotation constant. This experiment has 2 parts. In the first part, you will measure the period of a rotating mass. In the second part, you will determine the force required to keep the mass under uniform circular motion.
Okay, the experimental setup is exactly this one that you see here. Okay, it's a shaft that rotates. There's almost no friction here. And this shaft has a mass suspended from a string, and this mass is attached to a spring. Spring, okay?
Its most important element is its low friction rotating shaft. In the first step, you will insert a crossbar near the top of the rotating shaft. To firmly secure the bar, its beveled regions must face upwards. Using the locking bolt, lock the bar along the longest of these regions. The crossbar has a string from which you will suspend a rotating mass. A rotating mass is provided. This rotating mass is a bob. Measure its mass with a scale.
Okay, that's how it looks. That's how the bob looks like. And the mass of the bob is recorded right in here. Okay. The scale that we use has a resolution of 0.01 grams.
Using the provided spreadsheet, log this mass with the right number of significant figures. Suspend the bob from the string of the crossbar. At the base of the apparatus, there is an indicator rod. The indicator rod until its tip coincides with the tip of the bob. Tip of the bob to the tip of the rod. Using a ruler, measure the radius of rotation of the bob.
Okay, so the radius of rotation goes from this point where the bob is suspended to the center of the rotating shaft. And the radius, another raw data, goes right in here. Since we are using the same radius, all you gotta do is to repeat the same measurement for all. Oh, by the way, seven different measurements.
Take this measurement from the center of the rotating shaft to the tip of the mass bob. Log it in the spreadsheet. A spring is provided. Attach one end of the spring to the rotating shaft. Attach the other end of the spring to the mass bob. Hold the bob until its tip coincides with the tip of the indicator rod. Tip of the bob to the tip of the rod. While holding the bob, check if the spring is horizontal. If it is not, adjust the bob's height by either winding or unwinding the string attached to the crossbar. Remember, tip of the bob to the tip of the rod. Horizontal spring, vertical string. Lower the apparatus with the adjustable bolts until the apparatus' lower surface touches the table. Clamp the apparatus to the table with a C-clamp. Do not start the experiment until you align the bob, the rod, the spring, and the string. Also, ensure the apparatus is clamped to your table. This will prevent the apparatus from moving while you perform the experiment. Use your fingertips to rotate the shaft.
Here you go.
Adjust the shaft's angular speed until the tip of the bob aligns with the tip of the rod. If the shaft rotates too slowly, the bob will pass between the indicator rod and the rotating shaft. If the shaft rotates too fast, the bob will move past the indicator rod. Practice this exercise a few times with the rotating shaft before you start. Once you learn how consistently align the bob with the rod, you can start the experiment. Using a timer, measure how long it takes for the bob to complete 20 revolutions. Adjust the rotating speed to align the bob with the rod. Then count down from 5, 4, 3, etc. At 0, start your timer and continue counting the revolutions until 20. Because of friction, you may need to propel the shaft with your fingertips every now and then.
Okay, so the idea here is to measure how long it takes for the bob to undergo 20 revolutions, okay? With your timer. And remember, your timer has a resolution of 0.01 seconds, the one that we have in our cell phone.
When you reach 20 rotations, stop the timer, read the period, and log this value into your spreadsheet.
Okay, so that's the next. Just our next raw data, right? Here's the time. The mass of the bob, we already have it here, right? Here we are not adding any mass to the bob whatsoever. So that's our first set of data points. Okay. Then this, just keep in mind that this experiment has two parts. Let's see how to do that. This one here. Yeah, here you go.
As you count the number of rotations, ensure the tip of the bob remains aligned with the tip of the rod. Also, ensure the spring is horizontal and the string is vertical. If they are not, you may need to either increase or decrease the angular rotation. If you still can't achieve alignment, you will need to stop the experiment and realign everything. Load a 20-gram slotted mass to a scale and determine its exact mass.
Okay, that's the next measurement that you're gonna make. It said here 20 grams. Okay, I put there in the spreadsheet 30 grams instead. Okay. So what we are going to do, we are going to add 20 grams to the mass, to the rotating mass. Remember, we are varying the mass of the bob and keeping the radius constant.
Add this measurement to the bob's mass and log this result to your spreadsheet. Use the proper number of significant figures. Clamp the slotted mass to the top of the bob.
It's possible to clamp the mass to the top of the bob. Okay, the top bob that we have in there has a way to do that.
The bob is a disc with a threaded hole. Use it to safely clamp the slotted mass to the bob. Hold the bob to the left until the tip of the bob aligns with the tip of the rod. Make sure the spring is horizontal and the string is vertical. If they are not, adjust the vertical position of the bob by winding or unwinding the string. Put the shaft to rotate and determine how long it takes for the bob to complete 20 revolutions.
Again, 20 revolutions again. Here you go. So now is our second set of data points. First set of data points, second set of data points. And then we go keep on adding 60 grams, 90 grams, okay, until we reach 150 grams here. We are changing the net mass of the bob, and the period of rotation should change as well.
As before, the tip of the bob must be aligned with the tip of the rod. Compare this new measurement with the first one. Repeat the 4 previous procedures for 5 different slotted masses: 50 grams, 70 grams, 100 grams, 120 grams, and 150 grams, a total of 7 measurements. You will now measure the forces.
Okay, so that's the first part of the experiment. We determine how long it takes for 20 rotations whenever we change the mass of the bob. Okay, here what we do, we calculate how long it takes a single rotation, right? And then what are we going to do next? We're going to determine the force that's required to keep this bob lined up with the indicator rod. Okay, there's a very simple procedure to do that.
Spring applies to the bob. This force is equal to the centrifugal force. This part can be performed without the C clamp. Using a 1 meter long string, attach it to the left side of the mass bob. Pass the other end of string 2 through the pulley. Attach a mass hanger to the other end of the string. Load several slotted masses to the mass hanger. Load these masses until the tip of the bob aligns with tip of the rod. Also, check if the spring is horizontal and the string is vertical.
Do you understand what we are doing here? In order to find out what's the force that the spring is applying to the mass, which, by the way, is the centripetal force that this object is being subjected to, what we do, we load this support, this mass support with masses, okay, until everything is lined up here, and then you get this whole set of mass and measure their value with the scale. Okay, that's the hanging mass. I call that the hanging mass. And the hanging mass is what is being displayed right in here. 720 grams, 720 grams, 700 grams, and so on, okay? For this specific one. So here you go. Raw data, raw data, raw data, raw data, and all this, all the one that you see here is the raw data of the first part. And now the raw data of the second part, which is to determine the force, the centripetal force, is here. Yeah, just this one. Just this one. Okay, you mean the changes of what? Of the mass? Okay, the change of the mass is going to depend on your spreadsheet, okay? The change of the mass is going to, in my video, I put like 20 grams, 50 grams, whatever, right? In this spreadsheet, you know, I put 0, I put 30 grams, 60, okay, 90. The different values here of the added mass doesn't matter, can be different from one group to another one, okay? Is that clear, Basilio? Okay. Okay, provided, you know, the values, you know, the exact value that you added here that to the other math doesn't matter, okay? In this case here, in this spreadsheet, I choose 30 grams, right? In the video, I put slightly different values. Okay, so let's continue here.
Using a scale, measure the net hanging mass.
Here you go, hanging mass with the scale, 1/100th of a gram of resolution.
Mass hanger plus slotted mass. Log this measured value in your spreadsheet. Add the 20 grams slotted mass to the top of the box and repeat the 4 previous steps. Repeat this step for the remaining slotted masses: 50, 70, 100, 120, and 150 grams.
Oh yeah, that's right. It has to do with the group of students, okay? Remember, I have a total of 12 different spreadsheets. And what does it mean? It means that I had 12 groups performing this experiment. So each group may have chosen a different radius of rotation, okay, Basilio? So it's okay if your R is different from mine. And I encourage when we perform an actual experiment, I encourage my students to use, I encourage each group of students to use different radius for the rotation of their mass, okay? So yeah, I'm not surprised that your R is different from mine.
You completed the experimental part. Now perform your data analysis and determine if your experimental results are close to the theoretical ones.
Okay, so here you go. Let me shrink that. And now we got all the data. Okay. Again, I'm going to repeat raw data. Raw data. Raw data. Raw data. First part of raw data. And here is raw data, second part of the raw data. Okay, here we determine the period of rotation of the mass, which allow us to determine the velocity, tangential velocity of the mass. And here we found out what is the centripetal force, the experimental value of the centripetal force. Okay, so what you have to do, okay, we are going to verify if the equations for centripetal acceleration and centripetal force are correct. If the experiment, you know, is compatible with our theory. And what we have to do, here you go. Here are first and second part. We write down the equation for the centripetal force, which is mass times velocity. Okay. The velocity is going to be 2 pi r divided by the period, which, by the way, has already been calculated in my spreadsheet, right? The period of a single rotation is this period here divided by 20. Okay. Velocity is going to be 2 pi r divided by 3, by t, right? But when we do it in this mathematical way, we spell that out, everything. That's what we get for the centripetal force, okay? 4 pi square rm over t squared. And then what do we do next, right? We are varying the mass and we are getting different times, right? So what we are going to do, we are going to plot mass versus t squared. That's the graph that you're going to plot. Okay, when we perform, here you go, when we perform the experiment here with the hanging mass, we get almost the same result, almost. Okay, almost the same result. What does it mean? It means that the centripetal force doesn't vary as we change the mass of the rotating bob. Okay, there's a reason for that. There's a very good reason for that. We can do the free body diagram, and you can see that very clearly when you do the free body diagram. Okay, so what do? You're going to plot m. Let's see. Now we're going to plot this m here. Don't forget, it's not the hanging mass, it is the mass of the bob, right? Versus t squared. That's what you're going to do. You want the m in the y-axis and t squared in the x-axis, okay? And that's going to be a little bit tricky because you have to switch the axis. I'll help you out with that. When you plot this graph, you have, you know, here you go. Here's the theoretical derivation, right? You're supposed to, when you put m in the y-axis and t squared in the x-axis, you're supposed to get a straight line with this slope. Okay? Remember, the centripetal forces is not varying at much. And 4 pi square r is also constant. Okay, so when you plot the graph, you're supposed to get a slope that coincides with that ratio that you saw. Okay, so let's do that. You have only one graph here for you to do. Plot 1120 right now. You know, upload, download, measurement. Let's see. Plot m in the vertical and t squared in the horizontal. Okay. That's what you should be doing right now. We can do that in the next, what, 40 minutes, right? Like I said, you know, you gotta be a little, there's a little trick about this graph here. Remember that I told you everything that's to the right ends up in the vertical column, in the vertical axis of the graph, okay? So if you highlight that and this one here, you're gonna get t squared in the y and m in the x. So you have to find a way to switch that in your graph, okay? Otherwise, you're not gonna get the right slope. So go ahead, try to do that, and I'll be back shortly. I'm back. Let me see how you're all doing there. Attendance. 23. Let's see here. Blessing, are you there, Blessing? I don't see Blessing here. Brianna, are you there, Brianna?
Yes, I'm here.
Okay. Who else is here? Let's see. 23. We're supposed to have 24. Alejandra, are you there? I don't see Alejandra. Okay. Okay, Blessing is not here. Alejandra is not here. So we have Michael. Okay. We have 24 students, huh? Maybe someone is logging from two different places. Yesenia. Okay, so let's see. Let's go one by one. Vanessa, were you able to download the file? Yes. Okay, good. Were you able to plot the graph? That's the next thing. Maybe a little bit too early to plot the graph, right? Vanessa, did you plot the graph? Then anyway, let me know. Okay, good. Next, Fisher, did you download the graph?
Yes.
Okay, did you plot the graph?
Yes.
Yes, okay. So what's the slope you're getting?
1.31.
Okay, how does it match with your, what's the percentage difference that you're getting?
2.31.
Only 2%?
Yes.
Okay, so you put your slope here and the percentage difference they're getting is 2.31.
Yes.
Okay, did you put the m in the y-axis and the t-square in the x-axis?
Not yet. Oh, yes, I did.
Oh, you did. Okay, how did you do that? How did you do that?
I copy pasted both sets of data into adjacent.
Oh, that's how you did it. Okay, that's smart. I like it. Okay. So what you did, you copied this set of data, right? Let me
Yeah.
see. You put what, like that, right?
Yeah.
Oops. Let's not forget that I paste special. Okay, here you go. And then you get the t-square and you paste it all to the left of the other one, right?
Yes.
Okay, that's smart. Okay, that's one way of doing that. There's another way, but yeah, good. Congratulations. Okay, let's go for another group of another student. Okay, good. 2%, right? Slow percentage difference. You're getting 231%, right? Blessing. I don't think Blessing is here, right? Nope. Next is Janet Garcia, group number 2. Are you there, Janet? Okay, I don't hear from Janet. I'm gonna put a star here next to her attendance. Ryan, are you there, Ryan?
Yes, I'm here, Professor.
Okay, good. Did you download the spreadsheet?
Yeah, I just downloaded it. I just had internet issues.
Okay, so you didn't plot the graph yet, right?
Yeah, I'm in the process of doing it right now.
Okay, good. So next is Mia. Mia, are you there?
Yes, Professor.
Okay, did you download the graph, the
Yeah.
spreadsheet?
Yes,
Okay, did you plot the graph?
I'm plotting it right now.
Okay, working, right? Working. Let's put W here. Good. Raymond, did you download the graph, the spreadsheet? Okay, did you plot the graph? I'm going to assume not yet. Okay, you're still working on that. Let's put this way. Working. And Joshua, did you download the spreadsheet, Joshua?
Yes, Professor, I do.
Okay, did you plot the graph?
Yeah, I plotted it right now, but I'm not sure if it's right.
Okay, you gotta make sure that you did it in the proper way, right?
Yeah, I'm
Let
just
me-
trying to make sure I got the M in the y-axis and T2 in the X.
Yeah, because if you plot it like that, you know, you're gonna end up getting the t square in the y instead of the m, okay? In this case here, I have the t square in the y and the m in the x. I don't want that, I want the inverse. Okay, one way of doing that is to do what the other student did, right?
Yeah.
Yeah, it's just to copy those values here and put it in a bunch of cells right here to the right of the t square. That's one way of doing that. If you don't want to do that, there's another way of doing that. Okay, I'm going to do that for you. Here you go. Insert your group number
Be group number 3.
3. Okay, let me get your spreadsheet here. Group number 3 to see if we get the same. Group number 3 right in here. Come on. Here you go. I'm gonna plot Emma and t squared. Just like I said, you're going to get the m in the x and the t squared in the y, right? You don't want that. Did you get something like that?
Something in a bit similar, yeah.
Okay, so let's so at this very moment, you know, you have the m in the x and the t squared in the y. You can switch that. It's possible to switch that in Excel, okay? So how do we do that? Let me show you. I'm going to walk you through that. If you, in case that you don't want to do it that in the other way, you click one of the data points. Everything is highlighted. Right click, and then you select data. Highlight, select data. Okay. Here you go. Here's your series of data. You're going to edit this series of data. Note that the values along the x-axis are the ones in the column I. The I column is M, right? You don't want the M in the x-axis, right? You want it in this y-axis. So here you go. Notice that the L column, right? The L column for t square is in the y-axis. So all you have to do is to switch. What is L? Why it doesn't do it? Let's see what's going on here. Huh. Oh man, it's not misbehaving here for me. Let me try it again. Here you go. Edit. Let's see now. Huh. So odd. Okay, it's not working for some reason. Let me see why is that. Let me start from scratch. Select data. You go highlight, edit. It's supposed to edit. Okay, so it's not editing for some reason. Huh. Yeah, there's a bug here in my Excel. Okay, I do not know why it's doing that. Let me see. Let me see if I can do something else. Nope. Cancel. Oh gosh, that's frustrating. Sometimes Excel does those things. I don't know why. Let me quit that. Start from scratch. Okay. Hopefully it's gonna fix now. Emma and t square. Insert, plot, right click, select data, you know, one of the data points, right click, select data. Now, what about now? Edit. Okay, now it's working. See that? For some reason, it was not working before. I'm going to replace I with L and L with I. You know, here you go. L is I. So that's the other way of doing it, whichever you think is best. And now I inverted the axis. Okay. and we can double check if we have the values inverted. Is going anywhere between 0.3 to 0.5, right? In the x-axis, along the x-axis. 0.3, yeah, go to 0.5, so it's t squared. And what about in the y-axis? In the y-axis going anywhere between 0.4 to 0.6, right? 0.4, yeah, 0.4, 0.5 to 0.6. Yeah, we have it. Now you want to put the trend line there. Display equation chart, display r square, okay. And is that the slope that you're getting there? See if that's the slope that you're getting there, 0.9487.
Yeah, I kind of got something closer, not exactly
Okay.
that.
Yeah,
I
so
got,
you
I got 0.949.
okay, so that's because you inverted the axis, right? Let's see. You need to invert the axis. You should
Mhm.
get exactly the same slope. Okay.
Yeah, let me just rounded it, but yeah, I got close to that.
Yeah, let me plot in the other way, see if you get the same value in the incorrect way, right? Here you go. When I did those spreadsheets, I try to do everything in a easy way for you all folks. But there was this, okay, that's what I'm getting when we plot in the wrong way. 1.032, is that what you got?
No, I didn't get that. I got closer
You get
to
it?
the other one. Yeah.
Okay, you're group number 3, you said?
Yeah, that's correct.
Okay, I do not know why you're not getting the same value here. You're supposed to get the same value, okay?
Now just double check it to make sure.
Yeah, you're supposed to get the same value that I got because my data is exactly the same as yours. Okay, so let's go to the next student. Okay, Lily, did you download the spreadsheet, Lily? Hello, Lily, are you there? Okay, good. Now, wait a minute. I'm asking Lily, not Janet. Right? I'll get to you, Janet. Hang in there. Okay, I don't hear from Lily, so I'm gonna put a star here in her name. What about in her attendance, right? What about Michael? Are you there, Michael? Michael is not responding either. Okay, gonna put here a star in Michael's attendance. Let's go for the next one. Daisy, are you there, Daisy? Okay, oh yeah, in group 10, right? Let me put that here. Thank you. And oops. And did you download the spreadsheet, Daisy? Yes, okay. Did you plot the graph? Yes, good. Did you plot it in the proper way? Did you put the m in the y-axis and t square in the x-axis? That's very important. Okay, so what is the slope that you got? What's the slope that you got? We're gonna find that out right now. 1.577, right? So I'm gonna plot that for you. Group number 10. Let's see if it's 1.577. I'm gonna do it in the easiest way first. Attendance, no, it's not. Yo, my Excel is misbehaving today, folks. Let's see. Let's see, yeah. Okay, let me start closing some windows. Oh, finally. Okay, good. Now, t square Emma, right? Let's see if you got the right slope, Daisy. The slope that I'm going to get right now is not the correct one. Okay, if it matches the value, okay, so you got 1.57, so it looks like you got the right one. Okay, so let's see. Now let me invert to this one here. Select, right, series, you go. I becomes L, L becomes I. We didn't have this type of software during my time, okay, folks? Okay, see? Yeah, you got it right. Okay, Daisy, you got it right. 1.577, right? So let me delete that. So let's see. Attendance. Good. The next one, what's the percentage difference you're getting, Daisy? %, okay, 11%, 93. Okay, 1.577. Let me put there too. 1.577. Yeah, the theoretical value predicts is 1.42, right? 1.5771. Yeah, 10%, almost 11%. Good. Okay. So this, remember, this is the calculated the theoretical value, right? And how did I calculate the theoretical value? I took the average values of the theoretical force. Theoretical force is mv squared over r.
Very, very tough 2 months for me.
Okay.
And I'm just like, I'm
So
kind of
that
like
someone is
emotionally drained, physically drained for
Ryan?
the past 2 months.
Your mic is on. Let's see. I'm gonna mute
Oh,
you
my
again.
bad.
Okay. Thank you. Okay, so and then it's f it's a tripto divided by 4 pi r square, right? 4 pi square r square. Let's see here. Not this one, must be this one here. Slope, that's the slope. Yeah, 4 pi square r. Okay, good. So you did it right, Daisy. Let me see. We have 20 more minutes. Who is next here? Donia, right? Donia's next.
Hi, Professor. Yeah, I have the graph, but I'm still working on it.
Okay. So you did plot, right? But you didn't get the slope yet. Is that right?
No, I'm still trying to figure it out.
Okay. So do you need any help?
No, it's okay, but thank you.
Okay, good. So Jennifer Perez, group number 6. I guess having trouble with giving me a slope. Not sure if it's right. Okay. You are group number 6, right, Jennifer? Okay, so let me get your spreadsheet here. Group number 6. Group number 6. Let me see. First, I'm gonna plot in the wrong way. If my slope coincides with yours, then yours is wrong as well, okay? If it's not, then there is a very good chance that you got the right plot. So let me see. I'm getting a slope of 0.76. Oh yeah, okay. So you didn't plot it correctly, okay? Donia, Jennifer, right? So how do we fix that, right? Let me see if I can do this way. Sometimes Excel allows me to change. No, but most of the time it doesn't. Okay, so let's do that together, Jennifer. Click one of the data points. Okay. Make sure everything is highlighted. Put your cursor next to one of the data points and right click it. Then highlight, select data. Okay. And then click on series 1, edit. See? Series X values. That's column I. Column I is M. M is going there along the x-axis. So you change from I to L. Right? And you do the opposite to the other one.
Professor, can you do that again, please?
Yeah, let me see. Let me just finish it here. And then you change from L to I, right? So let's do that again. Here you go. Now I got the right the right plot. Okay, I'm gonna erase it. I'm gonna do everything from scratch. Okay. Who is that? Who is that who asked for help?
That's Alika.
Okay. Alika, right?
I'm in the same
Alika.
group. Yeah.
Okay, you're in the same group. Okay, so highlight M, right? Like I said, there's more than one way of doing that. Okay, there's more than one way of doing that. I'm doing this way here, so you can learn some new things about Excel, right? Highlight M, highlight T square, right? If I plot this graph, I'm going to get T square plotted along the y-axis and M along the x-axis, but I don't want that. I want the opposite. I want M along the y-axis and T square along the x-axis, right? So how do I fix that? Okay, you just swap one axis with the other. How do we swap one axis with the other? You click one of the data points in the graph, put your cursor there next to the data points again and right click. And then what do? You select, you highlight, select data. Okay, highlight, select data. Are you following?
Yes.
Okay, now what you're going to do, you're going to edit how those data points are plotted. Okay, so you highlight series and you're going to edit. Okay, you can do other things too with those things, but it doesn't apply to that now. Edit, and then notice here, series X values. This data here in this column I is being plotted along the x-axis. What's in the I column is the M, right? This data here on the L column, which is the T square, is being plotted along the Y values, the Y-axis. So what you have to do, you have to switch. What is I must become L. What is L? Okay, in this case, the L is going to be plotted along the x-axis. And what is L must become I. So everything along the I column is going to be plotted along the y-axis. Click OK, and now you have the correct plot. Now you have M along the y-axis and T square along the x-axis. Okay, and you can go ahead, put the trend line there and get the right slope for your graph. Okay, that's group number 6, right?
Thank you, Professor.
Okay, and let's see, 1.296. Let's see if we get it there. Not bad, right? 1.296. See that? The theory predicts 1.2547. So you're getting only 3% of difference. And remember, those are, I didn't make up this data. These are actual data that was collected by my students all those years that I have been teaching this course. Okay. So that's for group number 6. Attendance, Jennifer, right? Did I talk to Jennifer?
Yes.
Yeah, I talked to Jennifer, right? Okay, so Y, and did you get the right slope, Jennifer? Okay, well, let me see. We just talked to Alika as well, right? What about Pacheco? Arthur Pacheco, are you in good shape there, Pacheco? Did you download the spreadsheet? 1.296. Okay, good. What you're supposed to get, right? 1.296. And what was the percentage difference again? It was like 3%, right? Okay, so let's put 3% here. Good. Brianna, what happened to Brianna? Are you there, Brianna?
Yeah, I'm here.
Okay, good. So did you get everything there? Did you
Yeah.
download the spreadsheet? Did you plot the
Yes,
graph?
and all my data matches.
Okay, good. So now let's go for group number 7. Mary? 15 more minutes to go. Are you there, Mary? Mary is not answering me. Okay, I'm gonna put a star here on Mary's attendance. Basilio, You download the graph, Basilio, the spreadsheet. That is to match your example from earlier with those changes and with the correct axis. I got a slope of, the slope seemed a little bit too low, huh? Let me see. So you did plot the graph, but you're getting, let me see what's going on. I think this slope is too low, 239. What's the percentage difference that you're getting? Okay, group number 7, right? Let's go group number 7. Okay, group number 7. I'm gonna plot here for you, Basilio. T square M. Okay, insert. Here you go. Now let's see what's the slope I get. The incorrect slope, right? The incorrect slope is 1.53. Okay, with the original value, I got the slope. No, there's something wrong there. It's not 0.03. Are you plotting the right graph? Make sure you're plotting the right graph, right? Okay, Vahag is getting 1.53, right? So it looks like Vahag got the right one. So here you go. Let's. I'm curious to find out what Basilio did to get that strange slope. So here you go. Chart. You go. I'm gonna change it. Let's see if I get the same value as Vahag got. I becomes L, right? Yes, he's misbehaving again. I don't know why they do that.
Professor?
Yeah.
This is Basilio. For when I swap the graphs, because you know how it doesn't do the correct X and Y axis for the data. I swapped it a little bit of a different way, and I think that's probably what's producing the difference in the slope.
Okay, how are you doing? How are you swapping?
Well, when I right click on the axis, like let's say if I click on the vertical, the Y axis, and I click select data, and I just highlight the one I want. So I would highlight all of, just like we would normally do. And then
yeah, that works, right?
Yeah, I don't know now because maybe and then I press OK, and then I do the same thing for the other one, but I think I'm getting different data because of that though. So that's why I'm.
Yeah, let me try that. Let me try that. For some reason, my Microsoft Word my Microsoft Excel is misbehaving. Okay, let me close it. That group number 7. You know, every now and then those apps, they misbehave and you don't have a clue why they're misbehaving. Okay, and then you have just to reset them. Let's try it again. Let's see, insert. Okay, now I'm gonna do it in your way, right? Select data. Let's see. Edit. Yeah.
Oh well. Well, actually, I didn't even do edit. I just highlighted it like I did. I just highlighted the values itself. I didn't even change those values right there.
Really? Okay. So let me see. I'm getting. Let's see. Trend line. I'm getting 0.6315.
Oh yeah, you got much higher than me.
Okay, so let me see. Did I do it right? The question is whether I did it right or not. And Vahag said that he got 1.53, right? So let's see. Let's see if 0.6315 is correct or not. It looks like it is correct. The 27% off. See, that's the theoretical value here. So I'm gonna plot this graph again. Let's see if it's T square M insert chart data points, select data, edit L. Oh gosh, see that it doesn't do it. Okay, I'm going to assume that's the right one. Okay, let us do the other way, right? The other way the other student did. Here you go. Copy this one. I'm gonna paste right in here, but it has to paste the actual numbers, not the formula. I'm going to do the same here. If I do the regular pasting, I end up pasting the formula, not the actual numbers. Okay, so I have to paste according to, see, I have to paste the values. And now I plot this one on the side. What do I get for my slope? Yeah, 0.6315. Yeah, just like I got from the other plot. It's 27% difference. You know, this experiment, sometimes I have problems with this experiment. Well, I get those high percentage difference, and I never find out why we get that, you know. So that there might be some, you know, but 27, you know, is acceptable for now. Clear contents. Okay, so try to figure out, you Basilio and Vahag, why you are getting that values that are different from mine. Okay.
I just did it the way you just did, and with placing the X and the Y, just making another basically chart, and I was able to get the 0.6315.
Okay, good.
The same slope as you.
Okay, that's good. Okay, so it's just there's another way of getting the slope. Okay, here, you know, Excel has this function called the slope. Okay, equal slope non-y. The one that you want to plot in y is the m, right? Here you go. Highlight, and then we should get exactly the same slope, non-x. Okay. Oops. Now I have to put the right numbers there. Number 1, 2, 3, 0.6315. Okay? That's another way of getting the slope. Just by using the equation. We have 6 more minutes to go. Let's automatically runs out. Okay. Okay, so which other students should go for? But okay, I cover Basilio and Vahag, right? Alejandro is not here. I don't see Alejandra. Amarilis, did you follow what we did, Amarilis? We're running out of time, so I'm gonna go a little bit faster now, okay?
Yes, but I'm having trouble.
What do you say?
I said I'm having trouble.
You're in trouble? Okay. Do this now?
Especially that type of computer.
Yeah, you're breaking up.
Hi, Professor. This is Lily. I'm still working on mine. My Wi-Fi was going in and out.
One minute, we have multiple people talking at the same time. So, and I'm getting a backup from Marilis. Can you please type your message, Marilis, because it looks like there's some problem with your mic there. If you could type, it would be better. Okay, so let me go for another student here. Yesenia, are you there, Yesenia? 5 more minutes to go. I want to cover everybody here, so everybody has an opportunity to benefit from my help. Okay. Okay, so Yesenia, I don't hear from Yesenia. I'm gonna put a star here in her name. Justena, are you there, Justena? Justena Youssef. Okay, here you go. Okay, Yesenia replied to me. Okay, did you download the spreadsheet, Yesenia? Okay, did you plot your graph? I need to know if you plot your graph. Okay, I can't hear from you. Okay, so let's move on to Justena. Justena, are you there? Okay, I'm not hearing from Justena. Let's go for the next, Jade. Are you there, Jade?
Yeah. So
Okay,
for the
good.
slope, I got 0.88.
0.88.
Yes.
What's the percentage difference?
12.834.
Okay, 12.8. Let's see. And let your group number 9, right? Let's see here.
Yes.
If I get the same thing. Okay, so here go Emma and T square. Insert trend line. Yeah, okay, so it looks like you got the right slope. Now let's make sure that you did get the right slope. It's not reliable, the sync. Let me see here. Maybe this one is more reliable. Let's try it. Huh. Yeah, okay. So for some reason, this one sometimes doesn't work. I don't know why. Okay, so I'm gonna copy and paste. This one and T square. T square, here you go. Insert. Okay, this one, add trend line. I am getting 0.88, just like you did. Okay, good. Okay, Jade, so whatever you did seems to be correct. 0.88, and you know, the experimental value is 0.77, getting like 12% difference. Okay, so let's see next. Ashley, one more minute to go. Here you go. Okay, Ashley. Okay, you know, just interface with Jade. Okay, I'm gonna ask Labelud here since we're running out of time. Labelud, did you manage?
Yes, I'm here.
Yeah. Okay.
Yeah, I'm here.
Okay, what did you plot the graph?
Yeah, I do. I have 1.31, the slope 117.
And what is the percentage difference you're getting?
Just I just sorry, I just forgot to. Percentage wise is like 2.18.
2.18. Let's see. 2.18. Let's see here. I'm gonna slope non-y, this one, and non-x. I'm getting a slope for you of 1.30. That's what I'm getting the slope. You said you got, yeah, okay, same value. Okay, good. So you got the right slope.
Okay.
Okay, yeah, same thing. Good. So we run out of time here, and let's stop right now. If you want to chat a little bit more, I'll be available another 5-10 minutes here. And I see you next week, right? Don't forget Wednesday. Next Wednesday is the exam, is the third exam of the semester. And I see you next week.
Professor, for my name and my cousin's name for the lab for today, does it still have a star? Because we were here. We were just having internet problems.
Yeah, okay. So make sure you get a reliable internet connection, okay?
Thank you so much. They're doing construction, that's why.
Okay, so okay, so Any more questions?
Oh,
Yeah, I have-
Professor?
Yeah, who is that?
Oh, you could go, you could go, you could go.
Oh no, he can go because I have like my questions a bit long.
Oh, okay. Yeah, Professor, I just wanted to give you the slope of my graph because we didn't give you it.
What's your group number? What's your group number first?
Group two. Group two.
Group, right?
We didn't give you the slope because we were still working on ours.
Oh yeah, that's right. When you run out of time, right? Yeah, what was the slope you got?
Yeah, we got a 1.6857.
1.68. Okay. And how much percentage difference is that?
We got 36%.
36%. Let me see. Your group number 2, right? Let me check
Yeah.
if that's what we get. Group number 2. Let's see. Group number 2. Okay, so let's see. Slope M, non-Y, and non-X. Let's see if we get the same slope. I am getting a slope equal to number 1.6857. Is that what you got, right?
Yeah, that's what we got.
But yeah, that's right. Okay, the slope is correct. So it looks like you plot the right graph.
All right, sweet.
Okay.
I just wanted to let you know that because we didn't give you that information.
Okay, good. That's okay. We ran out of time, right? So I couldn't go back to you. That's okay. Okay, Labelud, do you need any help?
Yeah, I have one question because when I was formatting the graph for the other lab, the only way that I find like to erase the blank space, I changed like the axis instead of like starting at 0, 0. I start the axis more later.
So let me see, which lab report are you talking about? Number
Lab
3?
5.
5. Okay,
Yeah,
so I didn't correct lab 5 yet. So
Yeah, no, the only thing is that I want to know if like is the right way that I did it for like
let me see. I didn't check, so I do not. Your group number
11.
11. Okay. Let's see, group number 11. Lab 5. This one here, right?
Yeah.
Let me download
in
it.
In the Word document, I think it's
Open it. Oh, in the Word document, not in this Excel. Is that right?
no, because when I uploaded Excel, like the graph don't show exactly as
Well,
my
let me see. Let's check the Excel here in my computer. Okay. What doesn't show in the Excel document?
Okay, yeah, no, the only thing is when I see it in the drive, when I upload it, like I don't see it like that, like okay, the
Yeah.
only thing is that the graph, what I did because there was a blank space like before the line, so I just changed a little bit the axis to have it like really like zoom in.
Yeah.
Like you say.
Yeah. Okay. So yeah, I can see that you optimize the space, right? That's what you're talking about, right? Yeah. Yeah, you did optimize the space.
Okay,
Maybe.
so it's
Yeah. Let's see. Maybe you. That's okay. Yeah, this one's okay.
okay, so it's more like in that format that you are.
Yeah, that's right. No big blank spaces, right? No big blank spaces.
Okay, so the same thing for this lab 6 there.
Yeah, that's right.
Okay. Okay. Okay, thank you very much, Professor.
Welcome.
Professor, I had 2 questions.
Uh-huh.
So
Go ahead.
on Wednesday, the 30th, I'm not going to be able to attend lab because I'm going out of town. So I wanted to just like double check on attendance. Is it like you get a point marked off if you're absent once, or is it after 3 absences you get a point off?
Okay, so did you miss any other labs or just this
No,
one?
we're gonna still turn in our lab 6, I believe, we're still going to turn in our lab on time, but I'm just not going to be in Zoom that day just because I'm going to be on a flight. But we're going to still, like my group and we're still going to submit the lab. It's just I'm not going to be here in the Zoom.
Okay. Okay. So, okay, since you are not attending the lab 7, okay, the 30th of November is lab 7. Since you're not attending lab 7, you're not going to get credit for lab 7, okay? But if you turn in, you know, the report for lab 6, that's fine. Okay.
Well, we're gonna turn in lab 6, but the thing is, like, we're still gonna work on lab 7, like as a group, and then turn it in. So that's why I was gonna say, like, would I just like, why would I get 0 on lab 7 if I'm still working on it?
Yeah, because this is a synchronous class and you're required to be present for the lab. Okay.
Okay, is there like anything else I can do to make up for it? Just because the reason why I'm going out of town is for an interview for school. So it's something that I can't miss it. Like, is there anything I can do to make up for that lab in any way?
Yeah, if you check the syllabus, I dropped the lowest lab grade.
Okay.
Exactly for this type of reasons. Okay, if the student cannot attend a given lab, so I give a student a break by dropping the lowest grade of the lab. Okay, so if you take a look somewhere here in lab report, let me see here. So see, you know, since you're missing this lab, you know, I will drop this grade in the calculation of your final grade.
Okay. And then
I do that on purpose exactly because of those instances, but I do that only once. Okay, only for one lab report.
Okay. So do you think, like, in terms of my grade, like, I'll be fine if it's just that one lab?
Oh yeah. Yeah,
Okay.
you did all the labs, right? And that's the only one you're gonna miss, right?
Yes.
Okay, yeah. So you know, if you, let's say, if you get 100% on every lab and then you miss lab 7, you get a 0. You know, your average for the lab report is going to be 100% because I'm dropping the lowest grade in the calculation.
Got it. Okay. And then in terms of final grades, do you know when we'll know kind of what our grade was for every lab that we received?
Well, you already have the grades for lab 1, 2, and 3. Okay. So I'll be correcting lab 4 and 5 in the next few days.
Okay.
And remember, I cannot give you a final grade for the labs until I get all the lab reports, right? And,
Right.
And that's not going to happen until the classes are over.
Okay.
Okay.
Thank you.
Welcome.
Hi, Professor. It's Basilio.
Yeah.
I'm just curious because I want to make sure I understood the grades for the labs. I know Vaha was speaking with you earlier today, I believe.
I think so.
About the labs. That's what he had said.
Which lab? Lab number? Which lab number are you referring to?
The labs 2 and 3 specifically.
2 and 3. Your group number?
7.
6.
7.
7. Okay, Brazilian. Okay, so 2 and 3, right? Let's take a look at 2 and 3 here.
Yeah.
Did you see the correction?
I did, but I just want to make sure I understood them.
Okay. 6. Let's see. 6 corrected for lab reports. Let's look at 2 first, right?
Okay.
2 corrected. 7. Let's see how you did here. Did you? Oh yeah. See, you didn't get a good grade here in your lab.
Yeah.
Okay, that's because you see that you didn't do the significant digits, right? You left in the original format that I provided to you.
I'm changing that now, but I just wanted to understand why. So the digits are it, and then I know we didn't put the units there.
You're gonna put the units, yeah. Okay, note that, and then you also missed on the CL, okay? You also
Okay.
missed a bunch of things here, right? So yeah, you didn't put any of the units, and the units are very important, okay? That I take like 2 points out of every unit. So you lost like 24 points.
Mm-hmm.
Okay.
The
And
I have okay, so and then what's the 75 for? Is that how many points are missing then, I'm assuming?
That's right. That's how many points I'm subtracting is 100 minus 75. That's why you're getting this grade here.
I see, that makes sense. Okay. And then the other question was then, just to make sure I did this for the units, I don't know how always we're gonna get them, because that's why I get how to do the what's it called, where you only do 3 significant digits. I get how to do that. I just didn't apply it to there because I don't know why I didn't think of doing it to the other values. But for the units though, I always get confused on how to get the units, and that's why I was just trying to make sure I understood that.
Okay, so let's take a look. You're group number 7, right? Let's do that together.
Okay.
I'm gonna duplicate your spreadsheet. Okay, here you go.
Mm-hmm.
And I'm gonna just use the copy of your spreadsheet. Okay, all the units are all in meter, kilogram, and second, and every combination of it. Okay, I'm gonna use the main SI units. Some of the units already put that for you, like meter per second square, meter, right?
Mm-hmm.
All you have to do, L. What L? L is
That
a
would be
length.
meters.
Meters, yeah. Just put M in there. B was a length as well, right? The distance between those 2 points you put meters in there. Here, the Y is the same thing, right? Is the position of the photo gate. Then you put meters there, and T. Yeah, T is for seconds, right? X for meter. D, what's D?
D would be distance, right? No. Or
yeah, it's distance as well. Yeah, Y
so
minus
meters.
X, right? Well, so you put meters.
And then velocity though is D over T. So
that's right. This let's see, is L over T, right? It's L. Here you go.
Yeah.
Over T. L is meter. T is seconds, right?
Yes.
So you
just
put meters
M over
per second.
T. I'm sorry, S. Yeah. And then M over S squared.
Yeah. V square is going to be meter square over second square, right?
Yeah. Okay.
So if you want to make
I was just trying to make sure I understood.
Yeah. If you want to make it look nice, here you put this superscript there. You don't have to do that, but it's always good to know how to do that, right?
Yeah. I also noticed too, sometimes when we upload the files and then I re-download them, it doesn't show the graphs correctly sometimes, or it doesn't even show the graphs. And I just wanted to make sure you saw the graphs, correct?
Yeah, the way it works, every time that I download your spreadsheet, I see the graph the way you see, okay?
Okay.
What happens is that if you go to the, let me show you here too. If you're gonna go to your group, right? Group 7.
Mm-hmm.
Now, if you try to look inside your graph from the cloud, okay, sometimes it doesn't display the graph properly, okay?
Oh, and that's what it was.
It's from the cloud.
Yeah, this one had no graph, so that's why there's no graph.
Let me see. This one has no graphs, right?
Yeah.
Or that is. Let me see if you have. Yeah, that's right. This one has no graphs. Let's go for another one. Let's go for lab number 5, right?
Yeah, that one is we got to re-upload it. So
yeah, it looks like this one.
That's the original one.
Yeah.
We download our own copies and then we adjust them. So then this way we can compare and make sure we're the best one.
Yeah. So let me see. Let's take a look at lab number 2, right? Report for lab number 2. Must be, where is it?
Oh, you passed it. There you go.
This one we know that there is a graph there, right?
Yeah.
We know that this one has a graph. Okay. Let's see if we can see from the cloud or not. The Google Sheet is still not there, right? And because of that, you don't visualize everything. I have notes to that. Let's see, how do I zoom in and zoom out? Right in here. Okay, this one shows the graph. But it
just
look
looks
like
a little different.
Yeah, it doesn't show in the proper way. Okay.
And it doesn't show the regression equation and the slope and all that.
And this graph is not downwards. This graph is supposed to be upwards. Okay.
Okay.
So Google, they still have to fix that in their cloud. But when I download it to my computer, this problem disappears. Okay.
Okay. I was just asking because I know that the drop date is very soon. So I have to make sure I have I understand for the grades, because otherwise I won't be able to do too. I'm not doing too well, so I want to make sure I can do well. That's why I was doing all that.
Yeah. Which grade are you aiming for?
I was aiming for the B, but now I'm aiming for, I guess, the C. So we'll see what we get.
Okay. Okay. So yeah, just make sure you do everything they're supposed to do in the spreadsheets, right? I noticed that this last lab report, for some reason, students got a little bit behind, and they didn't do everything that they were supposed. It was not just you; there were other groups too. They didn't do everything.
Yeah. I'll do my best.
Okay.
Thank you, Professor.
Okay.
Bye.
Bye. Pronto, ok. Acabou. Agora, daqui a pouco. Clock 6 RT. I'll click this one at 12:30. Okay. Okay, one moment.